Today, our topic of discussion is on engineering asset longevity at blast furnace 3. Have you ever thought about what it would take to make a blast furnace essentially live forever? Here is the thing, we are moving from crisis prevention to waiting for the things to break to circular engineering. On the left, you see a cross section of our furnace with those blue pneumatic conduits snaking into the side. We are running at 12 bar of nitrogen to push 5 to 25 kilogram of material every single minute. And this is not just a repair tool, it is an IV drip for the furnace that target an asset life of over 20 years. But to appreciate that 20 years target, we have to look at the timer that currently ticking inside your furnace walls. So the ticking clock inside the crucible is the slide title. Here it has shown the carbon block in our crucible are like the brake pad on our car. They determine the absolute lifespan of entire machine. So look at the hexagonal block on the left. Those are pristine. But look at the middle section. That's critical erosion. Glowing breeze orange. By campaign year 10, the wall thickness dropped from 850 mm to just 310 mm, while the temperature spiked to a dangerous 1550 degrees centigrade. And this leads to a huge impact. When you hit that critical red zone on the data matrix, the structural integrity of your entire plant is on the line. And if you do not intervene when the wall gets that thin, the brick becomes much, much more than a maintenance headache. So, without intervention, hotspot lead to catastrophic disruption and which is quite obvious. What does an 82% risk look like to you? On the right, that massive orange tower represents the current trajectory of a furnace with a unmanaged hotspot. Now following the arrow on the left lead to molten pig iron leaks and total facility failure. It is just a total disaster, total mess. By switching to the green proactive healing strategy, we drop that catastrophic breach risk from 82 to less than 1%. So, how do we actually perform this proactive healing? And this is all our following slide shows. Synthesizing a proactive scab with the titanium. Think of this as a liquid bandage that turns into high-tech armor. In the first panel, we inject raw titanium. In the second, thermal bonding occurs where the titanium react with the carbon. By the third panel, you see that green crystalline titanium carbon scabs. So what it gives us, unlike regular carbon block that fail under hotspot contact, this scab can withstand prolonged molten flow, effectively relining the furnace from the inside out. To build that armor, we needed a delivery engine that can move solids like a high pressure heart. And the anatomy of a high pressure delivery engine, as it is shown in the diagram in the slide. So how do we move solid protection material across a busy plant floor for 100 meters? So it starts at the 15 cubic meter silo on the left, drop into a 3000 liter pressurized vessel and then blast through four separate lines, and these result into our resultant our expected results. This system allow us to deliver up to 25 kilogram per minute per line with the pinpoint precision right into the wind nozzles of the furnace. But shooting that much material at high pressure is essentially like sandblasting your own equipment. So, surviving the abrasive sandblaster effect is a challenge. Now, standard steel pipes would not last 3 months under this pressure. So look at the standard steel line on the graph. It crashes to zero almost immediately. But look at our ceramic lined cutway. It's filled with those green ceramic balls, and this is the real uh, result which is going to give us this injection system viable. Those spheres absorb the friction, extending the hose's lifespan from 3 months to over 5 years. Even with the best hoses, though, we have to watch out for system heart attack, what we call thrombosis. So, in our next slide, the threat of the pneumatic thrombosis. How we can air get a blood clot? If the moisture in the material hits 6%, it clumps into solid concrete like those white rocks you see at the bottom of the pipe. Our ideal zone on the scatter plot requires moisture to be under 2% and particle size under 2 mm. And this is a key. So if we hit that orange anomaly zone, the system suffers a total blockage and the protection stops. To catch those clots before they harden, we gave the system its own pulse check. So coming to the microwave Doppler radar for flow immunity. So we use microwave Doppler radar to read the pulse of the pipeline. Look at the activation curve. When the flow drops below 45%, the system senses a clot forming. At the 10% critical threshold, it triggers that green spike, an automatic nitrogen purge. And this is the effectiveness of the system. The system clears itself and restores 100% flow in just 2 seconds without any human operator needing to touch a wrench. So this intelligence means we can have very picky about the diet we feed the furnace. Now coming to the our injectability diagnostic matrix, we have three gates for success: size, humidity, and flow compatibility. These are really the pillars. So you will see that ilmenite or titanium source passes every gate, but look at rutile, it fails because of humidity. And this matrix allows us to qualify new material, ensuring we only inject what will actually protect the furnace rather than clog the system. And once the system gets clogged, it kills the entire supply chain and entire process gets fatal. So interestingly, some of the best material for our system are actually considered waste elsewhere. So coming to the our next slide, which is focusing on the taming the most abrasive plant waste. So dust collector waste is usually a disposal nightmare because it's so abrasive. Look at that ruined steel pipe on the left. But because of our ceramic resilience and 100% radar accuracy, we can re-inject that waste continuously. So we are turning a costly waste product into a free resource that helps save the furnace. And we are not stopping with the plant waste. We are looking at the city waste too. So from city garbage to carbon offset, imagine turning municipal plastic into a carbon credit. We take plastic waste, run it through a industrial shredder and inject the granules. And these destroy the waste and offset the traditional coke fuel, significantly lowering the overall carbon footprint of the operation. So when you add up the armor and the waste to the fuel, the impact on the furnace life is staggering. Now coming to the extending campaign life beyond 2 decades. This is the fountain of youth for the blast furnace. The orange line shows the original trajectory where the furnace was supposed to die in 2015. But look at that green line, titanium injected life, and this result a huge, huge effect, good effect. We have stabilized the wear and fundamentally redefined the physical limit of the furnace, pushing it operational well past 2025. So this has transformed our injection system into more than just a repair tool. So the ultimate circular economy engine about which our last slide sum up. So one architecture, three outcomes. As you can see, we have titanium for the acid protection, dust collector for the internal waste, and the plastic for the coke reduction. And all these system has evolved into a master tool for sustainable steel making. It saves the acid, eliminates the waste, and cuts CO2 all at once. This leads us to the final vision of what we have built. So coming to the engineering the future of the forge, this is the future of the forge blueprint. The system is online, asset health is stabilized and waste rerouting is continuous. But look at the future capability box. We are already prepping for the biomass and the charcoal. So we didn't just fix a hot spot, we built the foundation for the next generation of green, resilient steel production.